Alright, let's get started with Lesson 3, Le Chatelier's Principles. Now at this point, we should have a basic understanding about a chemical equilibrium state. That when a chemical equilibrium state has been reached, it means that the forward and reverse reactions are occurring at the same rate. And it also means that the concentrations are constant for both the reactants and the products. Now this equilibrium state should be maintained for an indefinite amount of time. However, we do have the ability to alter the reaction conditions. And when we alter the reaction conditions, it can cause a disruption or the breakdown of the equilibrium state. When this happens, either the forward reaction or the reverse reaction is going to go faster. And this is going to continue to occur until the system reestablishes a new equilibrium. But when we establish a new equilibrium, the concentrations of the reactants and products are going to be different than they were prior to the change in the conditions of their reaction state. Alright? Hopefully that kind of makes sense there. What we're going to do in this lesson is we're going to focus on what changes can we make to an equilibrium state, how does the system respond to those changes so it reestablishes a new equilibrium state. Okay? Now this process is applied to what we call the Chatelier's principle, which we're going to focus on here. Alright, so in summarizing what we just kind of talked about is chemists are able to shift the equilibrium position in a reversible reaction in order to suit the purposes that we need or have. We can do this by changing the conditions of the equilibrium state, which then are going to favor either the forward reaction or the reverse reaction before a new equilibrium is reached, where the product and reactant concentrations again are going to be constant. Now, favoring a reaction means that, as we mentioned, the reaction will suddenly occur at a higher rate than the opposite reaction, but eventually the opposite reaction will catch up and both reactions will again be at the same rate, forming a new equilibrium state, and the concentrations again will be constant. However, they should be at different levels than they were previously. Alright? Now, Le Chatelier's principle helps us to understand what a system does in order to counteract, you could say, the changes that we make on an equilibrium system. Alright? So Le Chatelier basically says this: when a system at equilibrium is subject to a change, it will respond in such a way to minimize the effect of the change. Another way of looking at this is that if I change something to the equilibrium state, then the system is going to try to do just the opposite. It's going to try to counteract what I just did in order to get the equilibrium state back together again. Think about it in this way. Say I add something to the equilibrium state, then what Le Chatelier is saying is that the system is going to do everything in its power to remove what I added. Okay, and you can kind of think of it in that terms. So what can we do to change the equilibrium state? Well, the first thing we can do is to change the reactant and product concentration. By changing either the reactant concentrations or the product concentrations, we will disrupt and destroy the equilibrium. The system then will respond to those changes by doing exactly the opposite of what we have done. And then once it does that, then a new equilibrium will be established. All right? That is so important for you to understand. Okay? So write this down in your notes, this little statement, and then we'll apply this principle. The changes in concentration of the reactants and products alter the equilibrium position, and so changes the composition. What we mean by composition is really the reactant and product concentration of the equilibrium mixture. But even though we change the concentrations, this does not alter or affect the value of Kc. And we talked about this in lesson number 2, that the only thing that can change the value of Kc is the temperature change. So concentration has no effect on it. All right? So let's apply Le Chatelier's principle to an equilibrium system. Let's look at this. In our notes, we have this equation. Simply, let's assume that an equilibrium has been established, that the rate of the forward and the reverse reactions in this system are occurring at the same rate. Therefore, the concentrations are constant, unchanging. All right? Now, for some time, this equilibrium state has been established. And then, at some point, we're going to add hydrogen gas. Okay? So we're going to alter the reactant concentration by adding more hydrogen gas. And that arrow goes up, meaning that we're increasing the concentration of hydrogen gas. All right? So, you're going to see a quick spike in the concentration of hydrogen gas. This is going to automatically disrupt the equilibrium state. The system, according to Le Chatelier, now wants to counteract this change. And so it says, hey, I don't like that you added the hydrogen gas, so I'm going to counteract that and get rid of it. Well, how can the system get rid of the added hydrogen gas? It would simply have to move the forward reaction in a faster rate. It'd have to speed it up. So to get rid of the hydrogen gas, it would have to literally shift the equilibrium position to the right. In other words, we would have to make more product in order to eliminate the hydrogen gas that we added. Okay? So simply this, by adding a reactant, is going to shift the equilibrium position to the right. And the forward reaction goes faster than the reverse reaction will happen. Now, once the system makes these adjustments and changes, then the system goes back to a new equilibrium state. However, the concentrations of both the reactants and products will be different. They will be altered from the first initial state before the change was made. All right? Now, we can see the same results if we add iodine. If I add more iodine, the system wants to get rid of the iodine, so it's simply going to shift the reaction to the right to create more product, to get rid of the iodine. All right? So, overall, these are going to be the changes that will occur. Okay? By increasing the iodine, then the hydrogen ion or the hydrogen concentration will go down, and the HI concentration will then go up due to the changes and shifts. Now, we also should see that the hydrogen concentration is going to also drop down a little bit from the added amount that we actually added. Okay? So, wait a minute. What about product, though? What if I add more product? What do you think is going to happen? So let's say we add more HI to an equilibrium state. Well, according to Le Chatelier, we want to counteract that, so we need to get rid of the HI. So to get rid of the HI, it's got to speed up the reverse reaction, and therefore it will become shift the reaction or shift the equilibrium position to the left to create more reactant. Okay? So that's basically what's going to happen, or the adjustments that will take place by the system when we add either reactant or product. Okay. Now what about removing? What if we actually remove hydrogen gas from an equilibrium system so that the concentration goes down? Well, Le Chatelier would say, if I'm removing hydrogen gas, then the system wants to make more of it. It wants to do the dead opposite. So to make more hydrogen gas, that means that we must change the product into creating more reactant. So therefore the equilibrium position should shift to the left, creating more reactant, and our product concentration should go down. And then a new equilibrium position should be established, or new equilibrium state. All right. I hope that makes sense. Let's look at this using a graph here. This might help out quite a bit. So let's rewrite our equation. We're going to take our hydrogen gas plus the iodine, and it's going to be in equilibrium state with HI. Right? So initially, the graph tells the whole story, really. And you should be able to look at a graph like this and interpret what's going on at any given time. Okay? So at some time 0, we've established an equilibrium. Now, how do we know that we're in equilibrium? Well, all the concentrations are not changing whatsoever, and the rate is constant for both the forward and reverse reaction here, as you can see by the straight lines from time 0 to time 1. Now at time 1 there seems to be a change. All right, what's the change? Well, it's because we added hydrogen gas, and it's indicated by this peak right there, that spike. And whenever you see a spike like this, it's a dead giveaway that's where the change occurred. And so we actually added hydrogen gas here at that point. Now, when that occurred, we should see a shift, or basically we should say the equilibrium is disrupted, it's been destroyed, and so the system is going to counteract that change to reestablish a new equilibrium. To do that, it wants to get rid of the hydrogen gas, so the reaction, as we know, should shift to the right. So if it's going to shift to the right, then we should see a decline in the hydrogen gas concentration. We should see a decline in the iodine concentration, but an increase in the HI concentration, in which we do. Notice that initially the hydrogen concentration goes up, and then it's going to go down. HI concentration also goes down as it reacts with the hydrogen gas, and then we're going to go create more product. The product concentration goes up. So from time 1 to time 2, this is where the changes are occurring to the system. And then at time 2, we reestablish the new equilibrium state. But notice that the concentrations are different in our new equilibrium state than what they were in the original. All right, the HI concentration has gone up compared to where it was originally. All right, and that's going to be typical of concentration changes that we're going to see. All right, so let's look at another one more. So here we have a reaction with nitrogen and hydrogen gas, and it's going to create ammonia. And let's assume that this system has achieved equilibrium. And we can see that by the graph here. Look really closely at our graph. We can see that initially we're at equilibrium between T1 and T2. We're in equilibrium state where the concentrations of H2, ammonia, which is NH3, and N2, they're all constant. No changes, therefore the rates are constant to each other. All right? But then there's going to be a disruption of the equilibrium between time 2 and time 3. So look at very carefully and see if you can find where the disruption occurred. What did we add to the equilibrium mixture in order to create a disruption to the equilibrium? Okay, look closely. You see it? All right. You should see a spike in ammonia. Okay, we actually added more reactant here, or sorry, product. My mistake. We added more product here. So what that occurred here is the ammonia concentration went up initially, as you can see. And then, according to Le Chatelier's principle, we want to counteract that. So that means that we're going to shift the equilibrium to the left to create more reactant. So that means we should see an increase in nitrogen and an increase in hydrogen and then a decrease in the ammonia during time 2 and 3. And we do see that. We see an increase in the hydrogen, we see an increase in the nitrogen, and we see a decline in the ammonia concentration. And then at time 3, we established a new equilibrium, and notice that the concentrations are much different at equilibrium. The H2 concentration went way up, the nitrogen concentration went up a fair amount, and the nitrogen or the ammonia concentration even stayed a little bit higher than it was originally. Okay, so that's the idea of what's occurred in these conditions when we've changed the concentration of our product. All right, so that deals with concentration changes. But what about let's say pressure and volume changes? Okay, this really more or less has to do with gases more than anything else, and that is changes in pressure will change or affect the equilibrium positions. Okay, so the idea here is we have a reaction between nitrogen and hydrogen again, producing ammonia gas, and we're going to look at changes in the pressure. All right, now when we kind of think about this for a moment, when the pressure increases, the volume of the gas should decrease according to Boyle's law. Okay, increase in pressure, a decrease in volume. Okay, so the fact is, let's write that down. Pressure goes up, volume should go down. Okay, now when that volume goes down because of an increase in pressure, it disrupts the equilibrium a lot. Now think about why, and that is because as we talked about in kinetics, when the volume gets smaller, then the concentration goes up of the gas, and when the gas concentration goes up, there's going to be a disruption of the equilibrium then. All right, so pressure changes disrupt equilibrium systems, and so therefore if I increase the pressure, according to Le Chatelier, it wants to do just the opposite. So if I increase it, the system wants to do what then? It wants to decrease the pressure on the system. Okay, now opposite of that, if I decrease the pressure, if I decrease the pressure, then the system wants to do the opposite, and it wants to increase the pressure. Okay, so how do we determine which way the equilibrium will shift if we change the pressure? Well, I kind of put a hint in your notes. Okay, an increase in pressure favors the side of an equilibrium reaction that has the smaller number of gas molecules. All right, again, make note that pressure changes do not change Kc. Okay, so let's look at this idea here about increasing pressure favoring the reaction side that has the smallest number of gas molecules. Okay, if I increase the pressure, I reduce the volume, the concentration of the gas goes up. All right? That means I want to do the opposite, or the system wants to do the opposite of what I did. So it's going to shift to the side where there's a smaller number of molecules, because that means the concentration would go down, and therefore it would reduce the volume. All right? So let's look at in terms of our reaction system that we have here in our notes. Okay? Let's say we're going to take and increase the pressure, right? And in which way would the reaction shift? Well, according to the statement, an increase in pressure should shift to the side where there's a smaller number of gas molecules. Well, on the product reactant side, we have 4 gas molecules. 3 from nitrogen and 3 from hydrogen and 1 from nitrogen. On the product side, we have only 2 moles of gas. Okay, so we have 4 moles of gas on this side and 2 moles of gas on the product side. Well, because the product side has the smallest number of moles, that means the equilibrium position should shift to the right, to the product side, for the smaller number of gas molecules to reduce the pressure. All right? Now, opposite occurs. If the pressure goes down, then the reaction is going to do just the opposite. It's going to shift to the side where there's more molecules. So in this case, the reaction is going to shift to the left to create more molecules of gas to actually cause the pressure to go up. Okay? So it's going to, remember, Le Chatelier is trying to counter everything we're doing. All right? Everything we're doing to the reaction is trying to do the opposite. So let's say this one more time. Pressure goes up. I would like to reduce the pressure now. Or in other words, the system wants to reduce the pressure. So to reduce the pressure, it's got to shift to the side of the smallest number of molecules. So in this case, it's going to shift to the right, to the product side, and that should cause an increase in the product and a decrease in the reactant. Okay? Does that make sense? So nitrogen then would go down, hydrogen's concentration goes down, and the ammonium concentration should go up when we make those shifts. Okay? However, the opposite is true. If the pressure goes down, then the system is going to shift to the left. That's going to create more moles of gas. That will then increase the pressure, so the nitrogen gas concentration should go up. The hydrogen concentration should go up, and the ammonia concentration then should go down in that situation. All right? So these are things you got to think about. Pressure changes can be hard. I think the thing that you need to think about is anytime I increase the pressure on an equilibrium system, the equilibrium is always going to shift to the smaller number of moles of gas. And if you can remember that, I think you'll have it down. Okay? So increased pressure, always shift to the smaller moles of gas. The reverse is true. If I decrease the pressure, then the equilibrium will shift to the side where there's more moles of gases that will result in an increase in pressure of the system to reestablish a new equilibrium. All right? So that's pressure in a nutshell. I guess the best thing to do is to kind of practice this and get used to it. But make sure you have this down in your notes at least, and so that you can refer to it and study it. And then we'll do some practice on this. All right, the next thing is temperature. Temperature effects on equilibrium conditions. Okay? what I got here is a reaction where we have a reactant that is actually turns the solution or makes the solutions kind of a pale pink. And then we have a product that creates a deep blue color, okay? Now, when it comes to colors in equilibrium systems like that, the color that is prevalent is the one in which the position of the equilibrium is more favorable. So if the equilibrium position is more favorable in the forward direction and the equilibrium lies to the right, then the solution should look deep blue, and we should have it should be product favored. However, if our Kc value is really small, then the equilibrium position should lie to the left, and the solution should look pale pink because it would be the greatest. Our reactant concentration would be much higher than our product concentration, so it look pink. Okay. Now, one thing to note before we get into temperatures, if this solution, let's say that the solution, the state that we're in, the equilibrium state, favors the products, then the solution should be a deep blue. However, if we add more product, it should shift. Remember, if we add more of this and this product goes up, then we should actually shift the equilibrium in this direction to create more reactant, and the product concentration should go down, and that should cause an increase in reactant concentration at the new equilibrium, and we actually should get a pale pink solution at that point. Okay, so by disrupting equilibriums and changing concentrations can change the color of the actual solution itself. Okay, well, let's go to temperature because that's what we're really here to look at. All right. To understand temperature, we actually have to look at the thermodynamics a little bit. We have to look at the delta H values, right? Now, according to this reaction, the delta H is smaller than 0. So that means that, greater than 0. So that means delta H is positive, which means that the reaction in the forward direction, is endothermic, all right? In the forward direction. Now the reverse reaction then, the delta H is going to be negative or exothermic in the reverse direction. So when you look at the thermodynamics, they're opposite depending on the forward direction and the reverse direction. Okay? Now, I think with temperature, to make it easy, because it's not easy to completely get it first. So what I suggest you do is you look at the delta H value. Since we know that delta H here is positive in the forward direction, then on the reactant side, I'm actually going to add energy on this side, okay, to my equation. Now, energy is not a reactant, and it's certainly not a product, okay? It's energy. It's not a chemical. But to make and understand Le Chatelier's principles during temperature changes understandable, I think that if you put energy on the reactant side, if it's endothermic, and on the product side, if it's exothermic, it's going to help you to solve these problems in much clearer fashion. Okay? Now that I did that, I can now think of energy as if it was a reactant or product. It really isn't, remember, but we can kind of think of it in that terms. And so, by doing that, it's going to have the same effect when we change temperature. All right? So, if I increase the temperature, for instance, okay, so the temperature goes up, that also means that the amount of energy also goes up. All right. Well, if energy is on my reactant side, and just as we understand with concentration, if I increase the amount of energy, then the system wants to get rid of the added energy, according to Le Chatelier. So that means to get rid of the added energy, the equilibrium position is got to shift, in this case, to the right, to the reactant side, or sorry, to the product side. All right? So think of temperature changes in terms of where energy is located at in our equation. Okay? So let's look at it in a different light. What if our temperature decreases? If our temperature decreases, then our energy will decrease of the system. And therefore, the system wants to create more energy. In order to do that, the reverse reaction has to go faster to create more energy, which really is shifting in the exothermic direction to create more energy. And you know that exothermic processes generate more energy. All right? So if you think of energy in terms of reactants and products, or like a reactant and product, then you can use Le Chatelier's principle in the same way or same manner as you would have changes in concentration. So in your notes, you might want to make sure you write this down as an increase in temperature causes an increase in the value of Kc. So whenever time we change the temperature, the value of Kc actually changes. Temperature is the only thing that will change the Kc value. For an endothermic reaction, and then it will decrease the value for an exothermic reaction. You should probably have this learned and understood, this statement. I'm going to actually underline or box it, star it, whatever. Understand that point really well. All right. Okay. Let's try one more. Oops. Let's go to a whiteboard now. Let's try another reaction on a whiteboard. Okay. Let's say we have, well, let's just do N2 plus H2, and it creates ammonia. I'm going to actually rewrite that again. So N2 plus H2, and that's going to create an equilibrium system with ammonia. Now the delta H for this, I'm going to write it right here. The delta H for this reaction is negative. It's exothermic in the forward direction. Okay? So that's your first telltale sign. Whenever they talk about temperature changes and how it's going to affect or shift the equilibrium, you need to look at the delta H again. So since I know that this is a negative and it's exothermic in the forward direction, I'm going to add energy now on the product side. Now if it was positive, then I would have added energy to the reactant side, because the forward direction would have been endothermic. Okay? But since the forward reaction is exothermic, I'm going to put energy on the product side. Now, I can now treat energy as if it was a reactant and product. So, if the temperature change goes up, that means the amount of energy also goes up, right? So the system now has more energy than what it wants, and so it wants to get rid of it, so it's going to shift this time to the left in order to lose energy, which is also in the endothermic direction. All right, it's in the endothermic direction, and you know that when we endothermic reactions take in energy, and so we actually will lose energy by the system. Okay, or gain potential energy by the system, but lose heat energy, I should say. All right, let's look at the opposite conditions now. Let's say the temperature decreases, therefore the amount of energy decreases, so we actually want to create more energy, so we have to shift it to to the side of creating more energy, which is the exothermic direction, which is shifting the reaction to essentially to the right at this point to create more energy. All right. That's simply how temperature adjustments occur or change. Okay. So I know this is a lot to think about and to learn about concentration changes and about pressure changes and temperature changes and how it affects the equilibrium position and concentrations. We'll work with this some more in class, practice some problems, and all that good stuff. Okay. The last thing we want to look at is catalysts. The good news is this: it's really simple. Simply a catalyst. If we add a catalyst to a system that at equilibrium, the catalyst simply does not change the equilibrium position. It does not shift the equilibrium left or right. Okay. All it does is basically allows the equilibrium mixture to achieve equilibrium faster. Okay, and like everything else other than temperature, catalysts do not change the value of Kc at all. Okay, so again, concentration, pressure changes, catalysts do not change the value of Kc. Only a change in temperature will affect the Kc value. Okay, endothermic reactions will cause the Kc value to go up. Exothermic reactions, as we stated here, will cause the value to go down. And so, as I mentioned before, this statement is pretty important that you know and understand. All right, I think we're going to stop here. The rest of this lesson we're going to discuss in class a little bit and finish it up. So this is it for now. Please review your notes and prepare for the quiz on this.